All right, so today we're going to be doing deriving the numbers or the degrees of freedom for a distillation column. And here are the components were listed in our problem here. Um, I kind of drew this out already just to give like a kind of visual look. And for my sake, for the problem, I covered up, I mean, technically they are the answers, but I'll do most of it is just checking at each stage so I don't add them all up wrong at the very end. And then for the second part here with the sections, there's typical sets of design variables. Eventually you'll see that the number of degrees of freedom for a column is 5. And then those are the two sets hidden behind our mascots here. So, well, my mascots, the plushies I have here on my desk. So yeah, kind of just get into it. The most important thing to note, other than like an ordinary distillation column, is that we have a splitter and a partial reboiler. So those will be important later on. I guess we can just get started here. Yeah. So, I mean, I won't follow it necessarily how it was written, but there was, I guess I'll just do how I practice it in terms of deriving. So we have our condenser at the very start. So I don't know, condenser. Essentially, we'll be drawing all these out and finding out what the degrees of freedom are. Essentially, our mass and energy balances. So shouldn't be something super new. What else do we have? So let me draw the condenser. It's just one stream going in. I have this thing on with shapes, so I don't know how that works. Okay. Condenser, and it has some cooling coil, a coil, like the cooling. So there's obviously some Q attached with that, and obviously there's a temperature and pressure at the system, and then one outlet stream, just one. So before we start, there's actually two ways we can sort of do this mass and energy balance. Well, mostly on the mass side. Why I did that? Okay, but essentially we can either supply a given whatever supply given molar flow rate, which I'll do for most of these problems, and then in the next one, I think the splitter I'll do in terms of the molar fraction. In which case, for each stream, there's a molar fraction associated with the number of components, C, which will denote as a C number of components, the variable C, and then there'll be a total flow rate. And then as well on the equation side, when we do degrees of freedom, we have variables and um, our equations, and then on the equation side, we'll have a sum of mole fractions is equal to 1, because that may or may not change going in and out of our system, the system being the box here, our condenser. So I don't know what the best way to, this might be a little too close, but move it down a bit. So we have condenser, we have two streams. Let's just stick with orange, why not? So for our unknowns, I'll do variables, but same thing as unknowns. We have two streams going in and out, so that's two streams. And then each stream has associated with it some number of variables. So like I mentioned, there's C, number of components. The number of components kind of didn't give myself enough space. And then we have a temperature and pressure associated with these two streams. So I don't know if we want to put, so for the condenser, it's going to be the vapor and the liquid. So this is vapor from the stage below. We know it's the first stage since the condenser is at 0, and this is our reflux and our distillate. So I'll just call it L0. I'll just call it L, since we kind of ran into this trouble before where we know it's not all of it is being returned as a reflux. We know we're taking out distillate, so I'll refrain from calling it L0. So with that, we have a temperature and pressure of each of these streams. So temperature and pressure, and that would be two variables. So for each stream, we have 2 times C plus 2. And then with our variables, we also have our system. So our system has some variables associated with it as well. We have the heating power. Well, in this case, it's heat being taken away with Q, Q of the condenser. And we have the temperature and pressure of the system. So those three are also unknown. So we'll add those. So I'll have heating, temperature, and pressure. And then we have our equations. I think that's all. Yeah. Our equations. So obviously we're trying to find, with degrees of freedom, finding the number of specifications we need in order to solve our problem here. So for the equations, we can start with, well, our mass balance. Well, there's a C number of components. So C number of components is indicated, or we can use that to our advantage with a mass balance. So with every component going in, it must come out. It's not staying in that condenser. We don't want it to overfill. So what goes in must come out. So therefore, there is a C number of our mass balances, since for however many components that are going in, there's a mass balance associated with each component. So maybe like, I don't know, what was our component last time, like benzene toluene. So a benzene toluene mixture going in, so there's two mass balances. The benzene going in equals the benzene coming out, toluene going in, toluene coming out. So hopefully that's not too over explained. Now we have our energy balance. There's only one of those. What else do we have? Yes, so our temperature and pressure. Usually with our in our class, or in this case, we're trying to simplify the case where the system has a different temperature and pressure than our inlet, but the outlet has the same temperature and pressure as our inlet, or not as our inlet, as our system, excuse me. So since the outlet stream is the same as the system, that's what we're saying. We're approximating it like that. In reality, usually it won't be that case, since with pressure that we have to think about the liquid dynamics, our fluid dynamics, in which case there might be a pressure drop. And then with temperature, there might be some heating losses. But in our case, we're just going to say that the temperature and pressure of this outlet stream is the same as what's inside here. So with that being the case, we only have one outlet stream. So with one outlet stream, we have, well, I don't know, we can call this a temperature pressure equality. So that's 1 and 2, temperature and pressure, and we have one outlet stream, so that'll be 2. So I think that's it. I don't think we're missing anything else. Honestly, the condenser is one of the more simpler parts of this. So if we add these up on the left-hand side for our unknowns or variables, we have, checking we're recording, okay. We have 2C plus 4, and then 4 plus 3 here. So 4 plus 3 is 7. So 7, and then we subtract our variables, or our equations from our variables, and that'll be C plus 3. And what we have is C plus 4. Now we can go check if this is correct with our little mascot here. So pull this down a bit. Awesome, C plus 4. I got it right. Honestly, yeah, it is. I know I mentioned earlier, it's mostly for my case, in case I make a mistake. There's no carryover mistakes here. I'm not taking a midterm or anything, since there's so many places we can mess up. So next, going down, I'll do the splitter. So I don't know. Did I use? Let's just use orange for all of this. I'll have a little dividing line. Yeah, splitter. So give a little quick drawing. We use white. So essentially, for the splitter, it's just one stream going in. Need a bigger desk. Is that fine? Bigger. One stream going in, and 2 coming out. So I can go ahead and label this maybe L1, L2, and L3. Again, I believe the problem says it's a liquid splitter with heat exchange, so there is a Q associated with this. I think most of the parts of the distillation column also have a heating element or a heating exchange associated with it. So again, we'll have our some heat, temperature, and a pressure of our system. I think that's all that's necessary to draw. So yeah, go ahead and do this again. So we have our, if we can see that, once again, our variables or unknowns. So now we have 3 streams this time, so it's 3. And remember, with every stream, we had C number of components, and I guess I'll just write this out, honestly. But it was C number of components, so that needs to be specified. So number of components. Honestly, it gets a little repetitive, so you might catch on here pretty quick. So C number of components, and as well as a temperature pressure, which basically means we have C, or three streams and C plus 2. Oh, I'm sorry. I think I said I was going to do this in mole fractions. So it's not just, so for 3 streams, we do have the same things, but in this case, we use molar flow rates. Did I say that? I guess I didn't specify. So I think I explained it earlier, but again, the difference between these two, well, I'm just doing it for the splitter. For most of these, I'm going to be using molar flow rates, so moles per second of each component. So that's why the C number of component, I guess I should have labeled streams or molar flow rates. But in this case, just to show what it is like with molar fractions, we have to also account for the fact that for each stream, I guess I could put this here too. So maybe equations, streams. So for each stream, there's C number of components, and again, temperature and pressure, so the 2 more unknowns. But with molar fractions, we also have to say that there's a total flow rate, so that'll be an additional, I don't know, flow rate. That'll be an additional unknown. And then with the streams on the equation side, we have the sum of all streams, so L1, L2, L3, the streams, well, the 1 stream going in and the 2 streams coming out, they all must have a sum of 1. And since that's how molar fractions work, they all have to be a fractional sum of equal to 1. So if we do a little math here, I mean, it's not that difficult. And actually, I wrote 3, and it makes sense now, but it's actually going to be wrong, and you'll see in a bit why. So I don't know, we have 3 C plus 3, and then 3 sum of mole fractions. Let's keep on going on the variables, the unknowns. Again, we have our QTP, our heating, our temperature, heating energy, our temperature and pressure associated with this system. So that's an additional 3 unknowns. I believe that should be all. And then with our equations, honestly, if you're blanking, we can always just look back, which I am. So yeah, mass balance, energy balance, and outlet stream. So mass balance, we have C for mass balance. For energy balance, again, we have only 1. And then for outlet stream, so again, we have 2 streams going out, but the temperature and pressure, again, we said these were equal to the system. So we have a temperature and pressure associated with this stream and another with the bottom stream. So that's 2 unknowns per stream, per outlet stream, and that makes 2 times 2 is 4. So we have 4 of this temperature pressure equality. And one different thing here is that we have a splitter. So we can write an equality where, well, essentially an equation where the, I suppose the mole fractions of each component in each stream of these outlet streams must equal the system. So again, I think it's specified here. I guess not. Well, liquid splitter. So it's the same liquid, I guess, is what we should be focusing on. So if the liquids are the same, it's C number of I don't know how we want to write this. Equal molar, since we have some mole fractions here, it's equal, I don't know. It's not necessarily, we'll be using another C term. I'm just trying to differentiate how this should look like with the other term, since that will be with equilibrium. And in this case, we don't have an equilibrium. It's just one phase going in and out, but it does have different molar fractions. And the equation we're trying to write is, or to represent this, I guess the number of equations is that these the molar fractions of the two outlet streams must be equal to this system in respect to, or I guess with respect to the number of components they have. So I don't know, maybe like equal system, I don't know, equal mole frac system as system. So basically what I'm trying to say is, I don't know if I should write this now. Well, I guess I should get to the point I was making earlier where this part was wrong, in which case we double counted a stream, since what this is saying is that the sum of mole fractions is equal to 1. Am I doing this correct? Yeah, okay. Sorry. So we have the sum of mole fractions, maybe n fractions or c, since we have c components. So liquid mole fractions for c components, and then we have 3 different streams. We have L1, L2, L3. So the one inlet stream, this has to be equal to 1. Remember, these compositions could be different. Well, I won't write that they're equal to 1. So again, same thing for the outlet streams, I should say. And now what we're saying is that since for this last component here, since the outlet streams have equal mole fractions as a system, these sums of mole fractions equaling 1 are actually the same for these two. So I don't know, these are actually, they're the same, and I'm just going to call them a different number, maybe L23. I guess not number, but label, and you'll see that the number of equations is actually decreased. If I rewrite this kind of visually, I know this helped me when I was trying to understand this. We went from 3 equations to now 2. So that's why that's the case. For this mole fractions, now it is 2. So that's the reason why this equal mole fraction of the system, we actually double counted that initial sum of mole fractions is equal to 1, since these two outlet streams, right here and right here, are actually the same molar fractions, since they both come from the same system. Okay, that should be enough over explaining. So if we do some algebra again, once again, see we have 3c plus 9 plus 3, so 9 plus 3 is 12. And then that's subtracted from, let's see here, so 2c plus 2 plus 1 plus 4, so 5 plus 2 is 7. And then this should be equal to, let's see, minus, so c plus 5. It should be 1 degree of freedom higher than our condenser. So yeah, c plus 4, c plus 5. Pretty sure I'm right, but it doesn't hurt to check. There we go, c plus 5, nice. All right, I think what we did next is the equilibrium. Honestly, if you're from class, you'll notice I'm doing it the exact same way we did it in class, so hopefully that helps. So the equilibrium stage, we'll do one of them first. The equilibrium stage. And now this is, think of this as one of the stages in our stack. Okay, this is pretty big, but one of the stages in our stack, and it could be either rectifying or the stripping section. And honestly, they're the exact same degrees of freedom, just differentiating between the number of stages. So, right, yeah, I guess we just write this through. So variables or unknowns. So now we have 4 streams. I hope the point gets across. It's usually, well, in this case, we had c plus 3 with the flow rate with the mole fraction specified. In this case, we're going back to flow rate. So the flow rates of each stream, and then we have temperature and pressure. So C for components, component molar flow rate of each stream, and then +2 for the temperature and pressure. Trying to shorthand this, I guess, not show as much since hopefully I explained it enough. And of course, with our equilibrium, I think it's also stated in the problem. So liquid equilibrium, vapor liquid equilibrium stage with heat exchange. So again, that has, well, a usual equilibrium will have temperature and pressure, but then we also have, in our case, a Q. So this could be heat supplied, heat transfer, just the heat in general. And then we differentiate that from energy. So that's another 3 from those 3 unknowns. Then we have our equations. Now this is where we have that second C I was talking about earlier, but let's go in order here. C for our material balance, again, component mole balance, 1 energy balance as per usual. It's only one system anyway. I think it's, yeah, right here we can just put, oh, I guess I should do it temperature and pressure equalities first. So notice that we have 2 outlet streams. Remember, our outlet streams are different from our or the same as our system, only the inlet streams are different. So that's the estimation we're making, approximation. So with 2 outlet streams, we have 2 temperature and pressure equalities with our system. Equal system. And then now we have our equilibrium. So that has C equations associated with that equilibrium. Essentially, Raoult's law. Remember, why? I don't know if I could just write equality, honestly. So that's Raoult's law, or we can write our liquid mole fraction of any component, and gamma, our activity coefficient if it's non-ideal, and our saturation vapor pressure for that component is equal to the fugacity. So that's the vapor molar fraction times the fugacity coefficient. I believe we use phi. And then just the total pressure. Yeah. And this equation can be written for, I mean, you see the I's, those can be written as C's. Again, just the number of components we use for our distillation column. So that has C equations associated with that equilibrium equation. And I think this is it, honestly. I don't think I'm missing anything else. So yeah, let's just do this. 4C plus 2, so 4C plus 8, 8 plus 3 is 11. We subtract. So we have 2C, and then this is 2 times C is 4, plus 1 is 5. And this should get us 2C plus 6. See if that's correct. Since if it's not, it's good we checked. Since we'll use it for our stack later on. 2C plus 6, nice. So we actually got all these right so far, nice. 2C plus 6, not bad. All right, moving on, we'll do our stack of stages. So again, this can apply to both the rectifying section and the stripping section, since it's essentially just these singular equilibrium stages stacked on top of one another. So I'll do 4 in this case to showcase an example, and then we could use equations to sort of model what this would look like. So I guess write what this is. So this is a, I don't know, equilibrium stack. Am I doing underlining? Man, I gotta keep organized here. Okay. Yeah, we have a bunch of boxes, honestly. Turned off the shape thing since it was getting annoying. Might be too big, but whatever. I think I said 4. Sure. So we have 4 stages here. That's really big. Okay. Yeah, let's go ahead and write our variables. So what we already derived is the degrees of freedom for one of them. So I'm going to put that here. And in our case, we'll use n number of stages to denote how many stages there are. So if there's 4 in this case, n would be 4. So keeping things simple, we have equations. And this goes with our essentially our double counted, so double count, I guess. So you notice that with our equilibrium stage, we account for 4 streams, but in our equilibrium stack, these 4 streams, well, they're accounted for in this. I guess we can number these 1, 2, 3, and 4. They're accounted for in these in number 1, but once we go to number 2, you'll notice that there's an overlap. So we have to account for this overlap somehow. Keep it colorful, why not? So obviously the ones that are double circled are double counted. So we count, I don't know, 1, 2, 3 pairs of streams that are 3 pairs of streams that are double counted. So that is, well, I guess I'll just write it here as an aside. So 3 times 2 equals 6. So 3 pairs, and you'll notice that n was equal to 4. So if we do something like n minus 1 times 2, we can get the same number if n was 4. So again, just a short little, I don't know, algebraic representation to show for any number of stages we'll be able to calculate. It's just the number of stages minus 1, and then you multiply by 2 to get the upcoming stream, the vapor stream, and the downstream, the liquid stream. So good, still recording. Okay, so that is n minus 1, 2 times n minus 1. And then remember, for each of these streams, again, for every stream, we always have to account for this C plus 2, the C, the flow rates of each component, and the 2, the temperature and pressure of each stream. So that is still a factor here. I think that's honestly it. Yeah, this may be too long. So let's just multiply this. So 2nc plus 6, so 6n, and then we subtract. I'll do this separately. So distributing across, you have nc plus 2n minus c minus 2. That's right. And then we have 2nc minus 4n minus 2n minus 4n plus 12. That's a c. Plus 2c plus 4. Rewrite left-hand side. And cross out what we don't need. So that cancels out. These subtract, so it becomes 2n plus 2c plus 4 degrees of freedom. So let's check that out if that's right. Here. Corrects me up. Okay, yeah. So the NR here is to specify the number of rectifying for, well, number of stages for the rectifying section. I think right under this is actually stripping, so let's go to that. Yeah. So you notice they can be different, so that's why we have to specify. They can be the same, but in the case that they're different, that's why we specify NR versus NS. So number of rectifying versus number stripping. Oh, I think I forgot to add, since I have plus 5, it's plus 4. Right, so I did forget. There's one thing that we are forgetting, and it is this plus 1. So this plus 1 comes from the degrees of freedom for specifying the number of stages we have. So we can choose a number of stages for degrees of freedom. And note that this degree of freedom unknown is not n, it's actually its own thing for the number of stages. So again, the number of stages is a degree of freedom that we can choose. So that's where this plus 1 is coming from. So again, it's not plus 4, it's 5. Again, this is different from the n. So this n component is coming from number of stages, but notice that this is per equilibrium stage, and it actually arises from, well, I guess I should say cancels out from specifying the Q, the heating component of each stream, and the pressure of each, or not stream, I'm sorry, the Q and the P of each stage, I should say. So that's why it's n stages. and we can cancel that out with 2n. So if there's n, 2n for each stage, we get rid of that by specifying the q and the p for n stages. And notice that this is two unknowns, so this is just 2n. So again, q is the heating component of each stage, and p is the pressure. A little water. Okay. 30 minutes. Where are we? I think we're almost done. Yeah, I think we just have the reboiler. So the reboiler is a little different from the condenser. Where's my pen? Okay. So reboiler. Last one of these. Reboiler. Yeah. So difference. Did I use white? Whatever. Okay. Reboiler, we have two streams coming down and then one stream going out on the side. That's our bottoms as usual. So notice that this is actually a partial reboiler. That's very important since it determines how we discuss the equation side for our degrees of freedom. So we have variables, 3 streams, so 3c plus 2, same old story. And then of course it's a boiler, there's a heating component. That's horrible. Okay, heating component and then temperature and pressure. So 3 more unknowns. Now we have our equations. Hopefully you're used to this by now. I think I have an aside with the... Oh, I am forgetting the feed. Whatever, we're here anyway. I can check this later. I think it's actually the same degrees of freedom as the condenser, so I shouldn't need to check. But anyway, with our equations, we have, again, our material balance, our energy balance, our outlet streams. So we have 2 of them, so that's 2 times 2 is 4. Remember, outlet streams have a temperature and pressure equality in our system. And then here is important because we didn't do this in the condenser, I believe, which is right. The condenser doesn't have an equilibrium relationship. Notice that there's not a second C associated with the equations here, but there is when we did the equilibrium. So right here. And is that the only one? Yeah. Now this is different from the C, the second C we used for our splitter, since that was equal molar fractions that we're taking out that are the same as our system. This other C is the equilibrium. So Raoult's law. I just put Raoult's. Okay. I'm tired. Raoult's. Sure. Raoult's. So that's equilibrium, and the same thing goes for our reboiler this time because it's a partial reboiler. So there is actually vapor and liquid in equilibrium at our reboiler because it's a partial reboiler. It's not boiling up all the liquid coming down. It's only boiling up some of it. So we have a C for our equations, and this is like what I said earlier, equilibrium Raoult's. Again, you can write that Raoult's expression for every component going in. So I think this should be it. So we have 3c plus 2. That becomes 3c plus 2. 2 times 3 is 6, plus 3 is 9. Subtract 2c plus 4 plus 5, or plus 1 gives us 5, so plus 5. And what do you know? It's c plus 4. So I was correct. Sorry, so feed is actually the last thing we're forgetting to do here. And also do a side stream, even though we're not doing it in this problem. Just good to know how to do it, because why not? We're already here. So feed, honestly, it's the same exact thing as a equilibrium stage. The only difference is that we have another inlet stream, so this is associated with C plus 2. And if you notice, with our equilibrium, what do we have? 2C plus 6 as our one equilibrium stage. So if you actually start with that 2C plus 6, and we note we have one inlet stream, well, we can just add that as an unknown, and that becomes 3C plus 8. But why believe that? Why don't we just actually derive it? So we have variables. As usual, now we have 5 streams. So 5 streams. Again, we're adding one inlet stream. That's the only difference. And this is still a heat exchange. I don't know what the exact words they use here. A vapor liquid equilibrium stage with feed and heat exchange. So heat exchange denoted by Q. Once again, so C plus 2, again, flow rates and temperature and pressure of each stream are 5 streams this time. And then we have 3 for our heating, temperature, and our pressure. Then for our equations, honestly, this is the exact same as our equilibrium right here. So, or you don't know when I say here. So right there. Honestly, the exact same. Can I just copy it? I could just copy it. Yeah, why not? Yeah, there's no extra outlet streams, so it's the exact same. Copy, paste. Bang. Okay. Okay. Sure. So what does this give us? We have 5C plus 10 plus 3 is 13. Subtract 2C plus 5. See if this is right. 3C plus 8. There we go. Exact same as what we got when we just started with our equilibrium stack. So let's go check this. That was the, I don't even know what that was. I already forgot. The feed. Okay, 3C plus 8. And now I think I said I was doing the side stream, because why not? So this is different. Now the side stream, down here. The side stream is, in addition with a heat exchanger and an equilibrium stage, now it is another outlet stream going out. So like so. And you'll probably already know this is a C plus 2 additional stream. But we do know again, remember when we took out with our splitter that relationship of C. So I'll just write it here, honestly. So we're subtracting C since we already know the molar fractions of that. Where's the splitter? Right here. We already know the molar fractions of these outgoing streams that we're taking out is equal to our system. And the components of those streams are the same as the system. So honestly, it's just right here. So this, I guess, equation or number of equations also applies to this side stream since we're taking it out. And we also know that this is a outlet stream. So the temperature and pressure we're saying, again, to be consistent, is the same as our, okay, come on, is the same as our system. So that's another 2 unknowns, I guess, gone. But there is one other unknown, and that is the flow rate of the stream. So you'll notice that even though we're adding a stream, we already canceled what we added out, but now we also have this one additional unknown, and that's our flow rate. So if I go back to our starting point, which was this 2C plus 6 for an equilibrium, all we have to do is just add that 1. Now we have 2C plus 7. I don't think I actually wrote this on my table, but it'd be nice if I did. Nope. Okay, well, there's a reboiler. C plus 4. Okay, so I think we actually have everything here. Honestly, I'm tempted to just copy this and add it all up. Since I already have it here, yeah, why not? Can I take this? I can. That's so cool. Okay. How do I want to do this? I can move everything out of the way. Here, let's do this. I'll move the condenser away somewhere to the side here. And bite that off and copy paste down here. I want to put it next to the drawing. Hopefully you heard all that. I want to put it next to the drawing since get rid of these check marks. Oh, I'll keep them. Well, I should cross this one out since we're not adding it. But again, with our degrees of freedom, we've calculated all these, derived them pretty much. Now all we have to do it for a column, we just add them all up like we did before. Though we do have to be careful, again, with our stack. Remember, we double counted some streams that were associated with other systems, or I guess stages. Same thing applies here. We are double counting multiple streams, so we just count the arrows in between each stage. That's a shared stream, I guess. So what do we have? We have 2 here. That's 2. 2 between feed and stripping, 2 between rectifying and feed, another 2 between condenser, splitter, and rectifying, and then this one with condenser and splitter. So that gives us 1 plus 2 is 3, plus 2 is 5, plus 2 is 7, plus 2 is 9. Okay, so we have 9 double counted streams. Remember, that will be C plus 2 for each stream. Again, component, molar flow rates, and the 2 unknowns plus 2 for temperature and pressure. So say that a million times. Okay, let's sum these up. I'm going to move this to the side so we can subtract this later on, just like how we did with our stack. Remember, we're subtracting away our double counted right there. So let's go back. So let's count our C's. Well, honestly, we can do the N's since the number of stages are separate. So we have 2, and I can just factor this out. Number of rectifying and number of stripping. Count all the C's. We have 1, 2, 3, 4, 5, 6. 6 plus 3 is 9, plus 1 is 10. So plus 10 C's. And then adding this up, oh boy. So quick maths, 4 plus 5 is 9. 9 plus 5 is 13. 13 plus 5 is 18. 18 plus 8 is 26. I'm missing one, no? Uh-oh. Here we go. 9 plus 10 plus 12. 11. Man, no, I can't just add. Okay, it's 31. I just can't add. Okay, and now we have our number of unknowns. So now we just subtract, honestly, right there. So subtract away our double counted streams. We have 9 C plus 2. That's equal to minus 9 C minus 18. So we keep our number of stages. Be consistent here. Our number for rectifying and stripping sections, and if you subtract 9, I don't know why I put equals. We have 1C and oh boy, 31, 18, oh, 13. Okay, 13. Now we have many unknowns for our degrees of freedom for a distillation column. However, I mentioned earlier that there's typically only 5 that we need to specify. And that's because all of these go away with the typical, I don't know, generic assumptions we make, or that we always give ourselves. So like I mentioned earlier, this term for the ends for number of stages goes away with our specifying the heating and the pressure of every stage, honestly. So that, remember, that was just 2n. And that'll apply to both the rectifying and the stripping. So I could put an R here and an R here, and I could do it again with why am I doing 2? Is it 2? Oh yeah, the 2 comes from this. I'm sorry, I'm getting confused. The Q and the P. The heating and the pressure. Sorry, I'm confusing myself. So those aren't, well, I guess technically there are 2, but the R should come from the number of stages. So right here. That's where I should be labeling them. Honestly, Q and P could be different between number of rectifying, number of stripping. So there is that as well. But just to not confuse myself, these get canceled out since we're subtracting these. I guess it shouldn't be really like that. Maybe an arrow. I don't know. So those are gone. Just cross this out. Then we're left with C plus 13. So here we go. I can write all of these out, honestly, or kind of running out of room. So I'll move this C plus 13. I'm going to write it up here. So C plus 13. first, we have our feed stream, so we can specify for that. Lucky for us, it's another stream that we didn't account for. It's, well, I guess we did account for, that's why we're subtracting it. It's an equation C plus 2 for our, so we have our stream flow rate, I guess feed, I don't know, feed mole flow rate, C, and then again temperature and pressure, so that's 2. C plus 2, that gets us down to C plus 11. What do we have next? We have the, honestly, I think I can do this all at once. So we have, I don't know, I wrote C again. Going crazy. Okay. Yeah, it's 11. Okay. Remember, we have for our stages, honestly, we're already done with rectifying and stripping. So all the stages we have left are the condenser, the splitter, the feed, and the reboiler. So those 4 stages. I'm going to hold off on defining the Q for the boiler and the condenser, since that goes along with the 5 degrees of freedom mentioned in the problem. So I'll do something like, where are we? 11. Okay. Guess I should circle it or something. So 11, we subtract 2 for our heat exchange and pressure of our, I don't know, which one do we want to do it first? Splitter. Then we can do it for our feed. And there's a reason why I'm specifying Q, not heating versus the, what is this? The feed. Versus the temperature, because notice the temperature is not something we should be specifying, because in a distillation column, each stage is at a different temperature. That's how we get our separation between our 2 components. So it's more the heating component. What temperature are we trying to achieve, or what is the not temperature, I'm sorry, the heating power associated with that stage is more correct. Okay, so we have splitter, feed, and then we have 2, but not for condenser and reboiler separately. Now it's just 2 pressures associated with the condenser and reboiler. See that? So that's 11 minus 6. We have 5. Those are our 5 that we have, or honestly, we were waiting for over here in our problem. So now we're on part 2. So this is more explaining. So I think I'm gonna move this all out of the way. Let's do that, and I'll move it all the way over here. So 5 degrees of freedom. What do we do? So with that, that's all our work. Nice. So with our 5 degrees of freedom, we can specify anything in our column. So we have to be careful and choose things that actually make sense, things that will give us a working solution, and things that are realistic and help us in the long run. So typically, I'll write these out, but honestly, they're covered by these 2 things. I'll write them out so I can explain them. Let's choose a cool color. So 1. Usually what is specified here is that at the condenser, so remember why I said we weren't specifying the cooling power and the heating power of our condenser and boiler. Well, these 5 degrees of freedom that we just derived are including that. So we have, for our condenser, we specify that it's usually at a saturated liquid. For our distillate and reflux, they're the same. And what this ultimately nets us is our condensing power, since if it's at the saturated liquid, that means it's in the liquid phase at its maximum density. It's at its bubble point. It's about to vaporize. So we cooled that vapor all the way down to its bubble point, essentially. So I guess I can write that bubble point. So that's the temperature. I don't know, bubble temperature, I guess. I remember all those things we did with bubble T and dew T and all that binary XY diagrams, all of that distillation column. So bubble point, the temperature, that is a specification that allows us to set our cooling power for our condenser. Number 2, so now we have our condenser. How do we get our boiler? So it's actually a little bit, I don't know, roundabout, but it makes more sense the more you think it through. We actually specify our reflux ratio. And the reason for that is that since we already have our cooling power and we know how much we want to condense, we set that bubble point and that temperature. So remember, reflux ratio is the reflux ratio is the liquid, the reflux over our distillate we're taking out. So we know how much we want to return and how much we want to take out. Again, that's the definition of our reflux ratio. So if we know how much we're essentially putting down our distillation column, that L0, if we know how much I'm not going to say it again. Why not? Yeah, if we know how much we're putting down, we should know how much we're putting up, since again, that's just a mass balance. So what goes down must come up. And with the distillation and our bottoms, well, we can always relate it to, since we know our feed, that's equal to our bottoms plus our distillate. And if we know our distillate and our feed, then we know our bottoms. And with our bottoms, well, not necessarily this way, but you can determine how much heating power you should put in with our reboiler. So that's where that comes from. So this is essentially just our power of our boiler. So now these next two are things we haven't talked about before. We're going to mention them here. So we have recovery rate of the light key. So this refers to one of the components, recovery of light key. So we use LK, and I'll just put RR again. So this is recovery rate. Remember, we use when we were setting the parameters of our distillation column, we always use recovery rate. That way we'd limit ourselves to, I guess, avoiding the error of a simple mass balance where we try to set a certain mole fraction, molar flow rate at our distillate, well, usually our distillate, that didn't correspond to our feed. So that's why we use recovery rate. And now we have these terms, light key and heavy key. So trying to explain these, we can use an example. Honestly, I'm ripping this straight from class, so kind of skip this if you remember already, but it was a separation of alkanes. So with that, I don't know, we can use C1, so methane all the way to pentane. I don't know if we went to C6, but essentially we separated these by choosing, well, where our split was. So we had a split, and you might be wondering, how do we choose this split? Well, it's determined by the pressure of our distillation column. With the pressure of our distillation column, we can choose, well, again, based on volatility. Well, if we have a really low pressure, even lower than what's keeping the methane C1 in its liquid form, if the pressure is lower than that, or I guess, yeah, lower than that, then everything has to be a vapor. So we have all vapor at extremely low pressures. That makes sense. Conversely, with really high pressures where we're condensing, well, not really condensing, but compressing, I guess, all of these together, all the particles together, we have all liquid. So everything comes down, nothing goes up. So those are the two extremes. And with our pressure, again, we use pressure since we can't have a constant temperature distillation column, since having multiple changing pressures within a distillation column is unrealistic and honestly not doable. So that's why we use our pressure as our constant, and the pressure is how we limit, or I guess choose our separations. And again, this is done via a flash calculation, usually, well, obviously preliminary, so we can determine the percentage of this separation. So I guess I should label these. These are the light key and the heavy key. So these are the two portions of this, I guess, multi-component mixture, C1 through C5 of alkanes, that are significant. They have, I don't know, significant partitioning. They have a greater percentage relative to the other components in the distillate and the bottom. So it would be something like, I don't know, 95% of the light key. Well, light key is predominant in the distillate. That's why it's the lighter key. It goes up. So I don't know, 95% in the distillate, 5% in the bottoms. And conversely, with the heavy key is dominant in the bottoms. So we have, again, conversely, maybe 95% bottoms and 5% distillate. And once we say this split, what we're also saying is that everything above this line goes to the distillate and everything below the split must go to the bottom, since the others are, I guess, lighter. In this case, C1 is lighter than C2. So, I mean, size plays a factor, volatility plays a factor. But that separation between the two, essentially we're saying that C1 has to go to the distillate and C4 and C5 have to go to the bottoms. And of course there might be, I guess, appearances or percentages of C1 in the bottoms or C4 and C5 in the distillate, but it would be negligible, something like 0.01, or maybe for C5 in the distillate, it would be like 0.0001. So obviously not significant at all. So distillate. So those are light key and heavy key explained. And then 5 is something that's not really, I don't know. It's just the common way we write these out, or one of the common degrees of freedom, I should say, and that is specifying the optimal feed stage. And this comes from the fact that when we set our rectifying number of stripping stages right here, which we crossed out, that was the degree of freedom we're setting. When we set those number of stages, essentially what we're saying is also where the optimal feed stage is. So with that optimal feed stage, that becomes one of our 5 degrees of freedom that we use as a variable specification for our distillation column. So that was one set. The other set is, well, they're hidden behind these two things, but the other set is, again, just instead of, well, not again, this is the first time I'm saying it. Instead of that, we replace the recoveries. So say we don't want to specify the recoveries. And again, all of these 5 degrees of freedom can be anything as long as they're related to the distillation column. And also notice, as an aside here, that we have 5 degrees of freedom, and no matter how many components we have, in this case I use an example of 5, that actually doesn't affect our distillation column. So again, we derived at the very end, we only have 5 degrees of freedom, but those 5 degrees of freedom could be anything we want. Right now I'm just showing you the more common ones. Other than this set of 5, there's a second set of 5. We just discussed this in class, I think, showed us in the textbook, but instead of the recoveries, we specify the number of stages. And I believe we also, instead of the optimal feed stage, we say the distillate flow rate. So let's check myself on that. Again, no need to memorize this. If you don't know it, you could just Google it, but here it is. I'm typing here. So yeah, I think that's what I said pretty much. So we have, I think we got all this right. So saturated, liquid, light key, and heavy key. So again, that recovery rate can be specified in the either the distillate or the bottoms. Pick whichever one you want, but recovery rate is definitely the better option, so we avoid that mass balance issue I explained earlier. Reflux ratio minimum. So specifying the reflux ratio not only ensures that we have a way to relate to our boiler, but also the fact that, remember, with the minimum number of stages with the previous video, we're actually able to run our column. We know how much, what the minimum, again, our minimum reflux ratio is, so we usually go up a little higher than that. I think I said a 1.5 or something in my last video, the last time I talked about this. And then the optimal feed stage. So this was a footnote in our book, and it just basically says what I said. The number of stages and the rectifying stripping that we specified earlier also, I don't know, introduce, or well, it says right there, introduction of this inlet is correspondent to that. So that's all that is. And then with this alternate I wrote in this third column, so a number of stages. Again, these are just what's most common. I guess the example we could say is I didn't want to specify this. I wanted to specify the mole fractions. Honestly, this is no more typing, it's just talking. So the number of molar fractions at a certain stage, that's legit. I mean, I could do that, but it definitely make things harder. So let's say I didn't want to do the number of stages here. I wanted to do maybe specify 2 components at 2 stages. And it doesn't have to be at the distillate and bottoms. It could be any random stage, honestly. But let's say it was at our distillate and our bottoms, sure. Those were 2 different compositions. Usually that's not the way to go, and the reason for that is because it makes it exceptionally harder, since now instead of specifying the number of stages, now when we go to do this in Python and specify the number of stage, well, now we're specifying composition, so molar fractions. Maybe I want the more volatile component be 95%, like in our example of the alkanes and the distillate, and then our I guess that wouldn't be, well, that would be for binary mixtures, but sure, let's use a binary mixture. We have 95% of our more volatile component I'm slurring my words. 95% of our more volatile component in the distillate, and the other component, since this is in our example, I'm talking out loud here, the binary mixture, the other component is 95% in our bottoms. So that's a specification I can make. If I did that, then when we do the root solver in Python, like we always do, these number of stages, instead of becoming a specification, now they're a parameter. So the reason why this is so hard is because the number of stages, well, those are whole numbers. Those are integers. They're not floating points. We can't have decimal places of a stage. So that's why when we try to find the root of that, remember that most of our root solvers, well, all of the root solvers, the equations, well, the outputs we've always gotten were floating points. They were never whole numbers. So that's why trying to find a root of a parameter that is a whole number is a lot harder than trying to find molar fraction of molar flow rate. So those are the types of things we would get or try to solve for given these specifications. And again, with reflux ratio and flow rate, say now we are specifying the feed stage, and now I don't want to specify these 2 down here. It's the same exact ballpark. While I could, so I say I specify the number of stages, now I have to solve for a reflux ratio and a distillate flow rate. And while we may be able to do that, it might not be possible. We might be solving for ratios and flow rates that don't make sense, that aren't realistic, or achieving a certain separation that is just not possible by specifying the actual composition and stages. So you might not have enough stages to achieve this molar fraction and composition at those stages. You might not have the correct flow rate. Your feed might not be able to keep up. So all these factors come into play when we try to specify things that aren't commonly specified. And the reason why they're commonly specified is, well, because they work, because they converge, and because they help us specify things that honestly make solving the distillation column a lot easier. So at this point, we have degrees of freedom, and we can actually solve our column. And sorry, I'm losing my train of thought here. I think in terms of actually trying to solve this, you would end up solving this with a root solver, like I mentioned before, and you would acquire molar fractions and molar flow rates of each stage. And well, you solve the column, but maybe those aren't the molar flow rates and the molar fractions that you wanted. So now you have to go and change all your parameters so that your flow rates and your molar fractions are exactly what you desired. And instead of doing that manually, now you do a root within a root and try to specify those parameters so that they adjust correctly. And now you're achieving the molar fractions and molar flow rates that you want. So see how this is very different, instead of something easy where it's like, well, I have a multi-component mixture. Well, that cracks me up every time. Okay. Instead of having, so if I have a multi-component mixture, I can't just specify, oh, I want this C1 to be this percentage at this stage, and specifying all those components at certain mole fractions at certain stages. It's just not realistic. At most, we can specify, again, the light key and heavy key. That's why we focus on those two, since those are the dominant partitions, the dominant, I guess, separations in the bottoms and distillate, and the rest just kind of comes and goes. So, yeah, I think this is pretty much the end of this. Did all these degrees of freedom, talked through all of them, condenser, reboiler. Remember, all of these were, well, most of them had a heat exchange, and then we added them all up to do our distillation column. We subtracted our double counted, and then we ended up with 5 degrees of freedom over here. And then these 5 degrees of freedom, notice that they weren't affected by the number of components we had, so we were free to choose whatever those 5 were, but these 5 were limited, well, not limited, but think of it as people have already discovered the most common ways or the easiest ways to solve a column, and it is with these variable specifications. So either saturation of the condensate, so our distillate, our reflux, looks like that's the common one. Reflux ratio is a common one. And then the other 3 are different between these two alternatives. One of them had the light key and heavy key, recovery rate, and the optimal feed stage, while the other one had the number of stages and a distillate flow rate. So those are, I guess this is the end of this. Yeah, I guess this last question, how is this consistent? Well, 5 degrees of freedom matches up. Honestly, that's the simplest answer. All right, so I think that's pretty much done with this. If you don't see me again after I pause this, then thanks for watching, I guess.